The purpose of this lab is to estimate the mass of a black hole given position and time data of a star orbiting the black hole, the star's mass, and the location of the black hole. In order to do this, we will instruct Python to manipulate the position data to provide estimations of the rate of change of momentum, use this information to estimate the net force, and then apply Newton's universal law of gravity to estimate the mass. In order to better understand how this method works, we must first understand a few key principles. As we know, the momentum vector is composed of its magnitude multiplied by a unit vector. Taking the derivative of both sides and using the chain rule on the right side, we can see that we can break up the rate of change of momentum into two components. One that is perpendicular to the object's motion and is responsible for change in direction, and one that is parallel to the object's motion and is responsible for the change in the object's velocity. Another useful property which comes from the momentum principle is that the rate of change in momentum is mathematically equal to the net force. There is a difference between the two that we will discuss at the end of the video, but for now we will focus on the application of this property. Finally, we need to know Newton's universal law of gravitation, displayed below. Since we are assuming that the gravitational force is the only force at work in this situation, we can say that is equal to the net force. How do we calculate dp dt? Since we cannot compute exact values of dp dt with what we learned so far, we must use the position data with a certain small enough delta t in order to estimate dp dt. Since we have data to work with in this lab, we have no control over our time step, and we must use the time in between position data, which is 86,400 seconds, in order to maintain accuracy. We can estimate the momentum between 2 points by finding their difference, dividing by delta t, and multiplying by mass. Then, once we have two momentum points, we can subtract them and divide by the change in time in order to estimate dp dt in that interval. Since this is tedious to do by hand, we let Python do it for us. When I entered the model into VPython, I had to format it in a specific way. I entered in the star's mass and the time step, then set a while loop that would calculate the initial and final velocities in the way described in the previous slide, later multiplying by the star's mass to convert the velocity values to momentum values. Then I defined delta v as v final minus v initial and delta p as p final minus p initial. Next, I defined dp dt in terms of previous lines of code and set fnet equal to this value. The tricky part was coding for the parallel and perpendicular values of dp dt. In the second slide, I derived the parallel and perpendicular components of dp dt, showing that p hat times the change in magnitude of p over the change in time was the parallel component. I defined p hat as the initial momentum vector divided by its magnitude, the rate of change of momentum's magnitude as the final minus the initial over delta t, and then multiply them together for dp dt parallel. To find dp dt perpendicular, I simply subtracted the parallel component of dp dt from dp dt itself. Notice how I set each component of dp dt equal to the respective components of fnet. I then ran the code to produce a model creating arrows representing the net force and its components. Notice how the parallel component is always in the direction or exactly opposite direction of motion. The perpendicular component is 90 degrees away from the parallel and pointed towards the center of motion, and the net force is both added together. To find the mass of the black hole, I took Newton's universal law of gravitation and rearranged it in order to solve for the black hole mass. I knew the value of the gravitational constant and the star's mass. VPython helped me find the radius and the net force. To find the radius, I took the final position of the star, subtracted the position of the black hole, and took the magnitude. Here you can see that I inputted the gravitational constant value, the radius, and the equation used to solve for the black hole's mass. I then used the print function to display the black hole's mass, which turned out to be roughly 2.97 times 10 to the 31st kilograms, about 15 times our sun's mass. I realized later that The calculated mass of the black hole could change based on which data points were used to estimate the net force, so I ran the above code inside the while loop to check all of them. The result was that all of the masses were well within 3 times 10 to the 28th of my estimate, indicating that there was less than 1% error and that deviation was probably due to round off. The net force and its parallel and perpendicular components are equal to the delta P over delta T and its respective components, but they are not necessarily the same thing. F net is what causes a change in motion, while delta P over delta T is an observed change that is measurable. Because of this, we can use delta P over delta T to reach the net force. If the original black hole was replaced with one of a different mass, the motion of the star would change due to the change of the gravitational force. Since we are assuming that the motion of the star stays the same, there cannot possibly be a black hole of different mass in the original's place. Thanks for watching.